Okay, next talk is quite interesting because it's a colleague that's presenting, Felix Wilhelm from ERNW, and he's also a very veteran Trooper speaker. The topic is attacking next generation firewalls, especially a specific product, but I won't give too much clues. So Felix, please.
Thank you. Hello everybody, welcome to my talk with the title Attacking Next Generation Firewalls, Breaking Palo Alto. Am I on? Hello? Hello? Okay. So, to my talk, Attacking Next Generation Firewalls, with the subtitle Breaking Palo Alto. So before we start with the actual content, a short introduction about myself. I'm a security researcher working for ERNW Research. I'm mainly interested in the areas of application and virtualization security. And in recent years, the research concentrated mostly on hypervisors with a focus on Xen. And in the last half year or year, also on security appliances, including FireEye and now Palo Alto. So, as mentioned already, Palo Alto is the target for this talk. So we take a look at a Palo Alto next generation firewall, which is running the PAN-OS operating system. So PAN-OS is basically the software stack that runs on all Palo Alto devices. And the device which I analyzed and which is also standing here, that's the one making so much noise, the blue one, is a Palo Alto PA500, which is kind of one of the smaller devices. But these bugs I'll talk about affect all of the different devices because they all use the same software stack, even if they have a much more powerful hardware. Today's main focus, again, lies on attacks against the device itself. So we didn't look too much into something like intrusion detection systems or functionality. Instead, we wanted to see what's the attack surface of these devices and how you can secure them against potentially advanced attackers or motivated attackers that target them specifically. When talking about what kind of features has this device, it's marketed as a next generation firewall, which basically means a basic firewall with some additional features. In the case of Palo Alto, this includes really powerful management interfaces. So you have normal SSH-based console management interface. You also have a quite interactive web interface for configuration, and you also have access to a REST API, so you can use centralized and automized management of all these devices in your network. In addition, it includes functionality for signature matching, so you have an intrusion prevention system, exploit detection, URL filtering. There's a feature called Wildfire, which basically is dynamic malware analysis in the cloud. You have AppRD, which means you can set up policies, firewall policies, based on the application that do the communication. So you are not filtering based on simply on TCP ports or IPs. You can do this on applications. And user ID, which is really interesting and is basically the same feature, but you filter based on user accounts. So you can say this user can connect to this IP or to this host. And then there's Global Protect. Global Protect is kind of a VPN functionality with additional features that are targeted to mobile devices mostly. So it's management of mobile devices and secure remote access of these devices. So of course, all these features can't be analyzed in a normal time frame. So we decided on looking at some certain ones of them. This includes the management interfaces, user ID, and Global Protect. So these are the three main topics we want to look at today. We didn't spend too much time investigating the other stuff, so I don't want to do any recommendations or any stuff on that. But for example, the application ID feature, we did a cursory look on that, and that looks kind of okay. So with this said, the actual agenda for today's talk, we start with breaking in. So as always, these kind of security appliances don't give you so even if you have administrative access, these security appliances don't give you access to the full operating system. And we need this access to perform the further research, which we present in the later parts of the talk. So the first step is performing a jailbreak. Then we take a look at the architecture of PanOS, and based on this architecture, we defined an attack surface where we again go to the 3 features or topics I already introduced. And of course, at the end, we have a short conclusion. So, starting with breaking in. The administrative interfaces, so in this case, we are the owner of the box, so we have full administrative access to the box. We just want to get like operating system access. And we have 2 interfaces we can work with. The command line interface, which is reachable over SSH and is shown to the left-hand side, and a web interface, you can just use your browser. We require this jailbreak to perform like the further research and understand how this device actually works. So we started looking at the command line interface. And the command line interface is basically restricted to like normal configuration and troubleshooting stuff, so you can review logs and you can look at stuff. And if you start playing around with this, you see that several of the command utilities you have are just like wrappers around standard Linux utilities. So for example, this test SCP server connection just calls down into the normal SCP program you have on every Linux system. And unfortunately, they don't escape all parameters correctly. So in this case, we just pass to this test SCP server connection command a host name that starts with a dash and includes a config option that's then passed to SCP or to SSH, so they use like the same configuration, which will define a proxy command that is then triggered when the actual connection attempt is made. In this case, our command simply changes the shell of the ERNW user from this restricted command line interface shell to a fully featured bash. So that's like the easiest approach you can choose, because then the next time you connect over SSH, you won't see the restricted interface. Instead, you get a full-blown Linux shell. When you do this, you quickly see that's it's a Linux system. And interestingly, it's a Linux system running on a MIPS 64 processor. And to be honest, it's the first device I ever had in my hand that's running MIPS 64. So it's kind of an exotic architecture, at least for me. And it's running a Cavium Octeon Plus processor, which has some kind of interesting features, as we will see later on. So the main focus of our research originally laid on the PanOS 6 version. So nowadays they also have a PanOS 7 version. So the vulnerabilities affect both versions, but like the architecture overview and the kernel version are for the 6th version. Interestingly, you can buy virtual appliances from Palo Alto, so appliances to run in the cloud or in your VMware environment. And of course, they aren't running on MIPS 64. Instead, they are like normal Intel x64 architectures. So this whole PanOS software stack kind of has support for multiple architectures. So there's definitely the possibility that if you buy like a different kind of box, maybe you get a different processor architecture. The network processing features, so all the standard like networking stack, is built on the top of the standard Linux networking capabilities. This is a good thing because there's nothing more like battle-hardened than the Linux networking stack. So it's much more, or it's a much better idea to just implement or reuse standard Linux utilities than writing your own TCP stack or your own IP tables firewall or whatever. Of course, there are some or many advanced features that can't simply be implemented using these mechanisms, and these are implemented on top as a proprietary Linux daemons. So this is a really high-level overview. It doesn't include a lot of stuff, but that gives you a bit of an impression what's running on the system. So as I said before, you have a Linux kernel as the foundation of the system. And then you have some kind of normal GNU Linux stack. So you have this normal user space utilities you can work on, you have shells, and you have an open SSH. So that kind of looks like a normal Linux system. But then you have these daemons running or colored in blue, and these are like the core parts of the PanOS architecture. So every one of them is like a core piece of this whole software stack. For example, like the cryptod is responsible for decryption and encryption of all kind of input. It also supports, for example, hardware security modules. So if you use a hardware security module, the crypto daemon will communicate with this. We have the master D, which basically is a watchdog that restarts and kills processes that misbehave. You have the sysd, which is a central daemon for the inter-process communication. So all these different daemons make heavily use of EPC, and they are all going through the sysd daemon. And you have the authentication daemon, which is deeply integrated in this whole Linux PAM stack. So this is the one handling all the authentications using SSH or the web interface, or even your VPN authentication. The IPC protocol that's spoken there is mostly XML-based, and it's used for a wide variety of use cases. On top of these 4 core daemons, then you have like the specialized daemons that are like doing a single task or responsible for a single feature. For example, you have the user ID daemon on the left top corner, which, as its name suggests, just is used for implementing user ID. One thing that's really interesting is a heavy reliance on a kind of software stack called Embed This App Web 3. This is an open source HTTP server optimized for embedded devices and is used to implement all web interfaces you can find on these devices. And they don't simply use this web server, they use this web server with PHP support and implement most of the functionality, if not all of the functionality of these web interfaces as native PHP extensions that are then in turn called by PHP scripts. So you have very small PHP scripts, like 5 lines long, that just call into a native PHP function, which is implemented in native code and compiled as a PHP extension. Now you might see web interfaces aren't that interesting, or why are there web interfaces on this box? Interestingly, we have 3 different web interfaces running on this box. For one, the management interface I already mentioned. Then you have the whole global Protect and SSL VPN stack is implemented and on top of this web server stack. And you have a captive portal, which is a feature of user ID I will talk about later. So when looking at this architecture and looking at the attack surface, then we can quickly see of course, we have the management interfaces. They are always kind of a popular attack surface, and if you see a lot of research on these kind of devices, you always see vulnerabilities on the management interfaces. They're kind of an easy target because most of the time they're pretty insecure, but of course, they should be on an isolated interface. So the practical relevance of these vulnerabilities isn't too high if you have a hardened environment. Of course, some of you work in big corporations and they probably know this isolation on these interfaces doesn't happen that often, so they're still kind of interesting. Now, even more interesting are these user ID and app ID features because by design, they operate on kind of untrusted network segments. For example, on guest Wi-Fis or network ports that can be reached easily by an attacker. So they are something that's more interesting for us as an attacker. And then finally, we have these parts of the functionality that by design are reachable by a completely external attacker. So of course, if you have a VPN, it's probably exposed to the internet somewhere, otherwise it wouldn't work. So this is like the really critical stuff, or if you find vulnerabilities in this stuff, it's starting to get really interesting. But we work from the top to the bottom, so we start with the management web interface. I mentioned that before, but we have a web UI that's used for manual management and the REST API for this automated access. So you can like script your own management clients or use software for that. All of this is implemented on top of App Web 3 and it's a PHP environment. And like if you pass this login screen, then you have like a lot of features available. You can configure the complete device. So of course, this is like a gigantic attack surface, but luckily, most of this requires authentication. So without authentication, you don't really have that much to interact with. The REST API, on the other hand, can be reached if you post a request to the /API URL. And the first thing that will happen if you call this /API URL is that this request will pass to a native function, which is called API wget-filter, so the webget utility from the name. Function, and this happens before any kind of authentication occurs. So this is functionality, native PHP extension functionality that we can reach completely unauthenticated. And then they do some kind of, so I honestly, I don't understand the mechanism completely because it's kind of strange, but if your request you send to this URL contains the get parameter client equals wget, then they use curl internally, so the Palo Alto device calls the curl command on its local system and checks against an internal service to like perform the actual authentication check. Now, this curl command uses or includes user input. In this case, it's the key request parameter, HTTP authentication headers if you send them, and the remote IP, so the IP you as a user have. They can use the TCP IP, so like the IP that originates from the network stack, but if you set the X real IP header, the HTTP header, they use this one instead. That's of course not ideal because this HTTP header can be easily faked by an attacker. It's just part of the HTTP request, so we can put an arbitrary value in there. Now, they don't simply pass them, they also escape them, luckily, otherwise it would be too simple. So they have like a single quote at the end and a single quote at the beginning, and all the single quotes in there are escaped, so that kind of works okay. But if you look at how this function actually performs its work. So this is not official source code of Palo Alto. It's just a pseudocode representation in Python-style code that does more or less the same thing the original code would do. And we can see, we check if we have this key parameter. If we have it and it's escaped, but this escape shell argument function returns something, a negative number, so it indicates an error, then we abort the connection. We do the same for the basic out header, but the interesting thing is that this does not happen in the same way for the HTTP X real IP header. So they still escape it, but the return value of this function is never checked. So how can we make this function fail? If you look at the second argument, it's 1024 bytes, and it turns out this is the length of the output buffer. So this is the length of the buffer where the escaped value is written to. Now, if you send a really long HTTP header, real IP header in there, then the escaping function will fail because the buffer won't be long enough. And if it fails, it behaves in the way that the single quote at the beginning of the value is in the buffer, but it will never write the single quote at the end of the buffer. So you have like an off by 1 in the single quoting. And this opens then the simple command injection because the key value should normally be escaped with a single quote, but there is a single quote missing. So instead, the single quote that's implemented or embedded before the key parameter closes like the first quotation, and then we have a direct command injection that we can use, for example, in this case, to create arbitrary files. This is pre-authentication, and it's a completely remote command execution against the management interface. Now, there's a reason why I have this big box standing down there, so I can do live demos. It's kind of a really not that simple setup, so some of them might fail, but I'm hoping it's working for now. So we just open up a shell on our local system, and we connect to the, so this is the internal IP. So if you see a IP with 1.1, so the ones are like the internal IPs. Later on, we will go to an external IP, which will be included by the 2. So this is one that we can just reach if we are actually in the management network segment. And if we start the exploit, we directly see we get a reverse connection and we have a shell running on the system. Thank you. And so it's running with nobody, right? So they make this, that's a good hardening measure. They're like the web server's running as nobody. We have a local privilege escalation exploit at the end, so don't worry about that for now. But it's good defense in depth, so that's really positive. And you can see like the Linux kernel running on our test device. And funnily, the actual request is kind of simple. You basically just send something like this. So we send an X real IP header with a lot of A's. It has to be a post request, but the post content is like irrelevant. And then we just, so the key, this is like URL encoded, but this includes directly the command injection I just showed on the last slide. So that's the first result. It makes you kind of hopeful you find more in this box, and it's like it's unauthenticated and 100% stable, so that's always a good thing. But in a hardened environment, it shouldn't really work. So hopefully you wouldn't be able to like exploit this. The other attack surface that we have seems to be much more interesting. So let's look at user ID. And user ID is quite interesting because it's one of the main selling points of the Palo Alto devices, and it's actually a really cool feature, so it's really useful for a lot of administrators. The idea is you can implement your firewall policies not based on like IP addresses or network segments. Instead, you simply write your rules something like this. So you can say if the user Bob at corporation, so Bob is your main administrator, he should be able to connect to my domain controller on the RDP port. And that should work, so that's the idea of user ID, irregardless of the IP address Bob has or which device he uses, or if he's coming over VPN or sitting somewhere in the office building. And of course, I think everyone who has ever managed like networks should agree that that is a kind of a cool feature. So you want to have that in your environment. So the next question, of course, how is this implemented? How are they going to do this or to support this? And the core idea of user ID is that you always need to have an active mapping between the IP addresses and the active user account. So you always need to keep this mapping somehow alive. And there are 5 main ways this is supported, and we just go through them one by one. So first of all, we have server monitoring agentless. And this is quite simple. It's also kind of not too terrible from a security perspective. So all the examples are like based on an Active Directory infrastructure. They also support just basic LDAP and stuff like that. But for simplification, we talk about Active Directory. And you just create a dedicated user that can log into the domain controller and read its event logs. It shouldn't be a domain administrator, but it has to have the server operator permissions, which are kind of, it's an interesting permission set. And it can be used to connect to the domain controller and read the event logs. You have to store the credentials on the firewall itself, so on the Palo Alto appliance, so the appliance can connect in regular intervals, read the event logs, and then like create this mapping between IP address and active user account. You can use the domain controller for this. You can also work with the Exchange server, so like the mail server or something where a lot of people regularly log on with their Windows credentials. That's kind of a simple mechanism. The problem is, of course, you now have like domain credentials stored on the Palo Alto devices. That might not be ideal if you have a different bug to like pop the device or the appliance, and then you can use this for further attacks. And of course, it doesn't really scale. If you have a really large amount of these different devices or these different appliances, and every one of them needs to connect to the domain controller, then it's probably kind of a lot of processing going on. So the next step you can do is you do server monitoring, but you include a user ID agent. So this is simply a Windows binary that's provided by Palo Alto. And you can install that on an arbitrary server in your Windows environment. And it opens a connection on TCP port 5007, waits for incoming connections from the Palo Alto firewall, and then goes to the domain controller and performs basically the same step the Palo Alto firewall did before. So we are still in an ongoing disclosure process regarding this user ID agent, so I won't provide any details, but our recommendation is to filter this agent. So the only one that should be able to connect to the agent is the Palo Alto appliance, so that's a good defense in that measure. So you might not want to use the agent, or you don't want to use server monitoring, so you can also use the captive portal. The captive portal works by looking for connections to port 80 or 443 if you also have like SSL interception enabled. And then you basically something like this. You see this user identification portal, which just wants you to log in to the website. Again, we are in a disclosure process regarding the captive portal. Of course, what I just want to say is, again, we have this AppWeb3 web server, and we have PHP extensions, which pose a significant attack surface. Yeah? So you should keep this in mind if you use the captive portal. And of course, one problem with this captive portal is that it might be just not feasible. So if you have a device that never uses HTTP or HTTPS, then you will never use the captive portal. And solely relying on the event logs on the domain controller is also not kind of the best way, because they might be stale, they might be old, it might need a lot of time until the user logins again, stuff like that. So they have a feature called client probing, and as the name suggests, it does exactly this. So you try to connect to something through the Palo Alto appliance, so you want to connect to some kind of filtered port, and the Palo Alto basically asks the Windows Server agent, or it performs the operation itself, but the idea is the client is asked, hey client, what's the user, or what's your currently active user ID? Some people might already think that doesn't sound like it's completely secure. Interestingly, it's enabled by default. It's based on NetBIOS or VME, and it just works like that. So if you connect to a device that had user ID enabled and client probing, you will see that the device is just connecting back to you, logging with stored credentials using NetBIOS or VMI, and asking for the currently active user. So that leads to a number of problems. One I find really interesting, this is research done by Rapid7 and H.D. Moore in this project Sonar release. They performed a large scan of like the whole internet, and they noticed they get a lot of connection attempts. So they see connections going to the scanning boxes over NetBIOS and VMI, and they see these connection attempts include credentials. And if you look at the user IDs and like so you get password hashes out of that, and if you look at that, you see, oh, they all have something to do with Palo Alto. And that's because some administrators enabled client probing on the external interfaces. So they have an interface that goes out to the internet and then decide, oh, I see a connection attempt. Let's check if he's a user in our domain and go out to that domain. Of course, this is not a classical security vulnerability in this device or in this feature. It's just a misconfiguration. But still, that can happen if you just click all the boxes. Now, even if you configure it correctly and it only uses you use it on internal interfaces, it's still, I mean, imagine you have a Linux server or a Linux client and you're in this network. And now somebody connects to you and asks you, hey, what's your Windows domain user account? There might be a possibility I just answer you something I'm just thinking of right now. So I have a demo for that. And this demo is kind of, so the problem is you can't be really sure when the client probing decides to come, so it might take a while, it might not happen immediately, but I'm hopeful. So I can show you, so what I'm looking at here is I'm on the command line interface of the Palo Alto devices, and I show this IP user mapping, which is the mechanism used by user ID. And we can see from my IP address at the moment, there's not any record, so I'm not logged into any Windows domain. So what I'm now going to do, so I start this magic Python script. I'm not going to tell you exactly what it does, but it uses the impacket library, which might give you a hint. And on the bottom, I'm just going to trigger some connection to the device. So this is like, this will trigger, or will hopefully trigger the client probing event. So I just try to connect to port 123, which will fail or time out because it's filtered. And if I now wait a couple of minutes, hopefully we will see that I get a IP user mapping. As I said before, this might take a couple of minutes, so I'll probably just continue with the slides, and then we will see there it is. Oh, whew, luckily. And now we can see I'm the user Felix at the domain fishbowl.corp, and of course, so I'm not even restricted to a single user. I can send I'm all these users, like hundreds of them, And if you find a single user that has like the permission to connect to every device, I mean, all of you guys probably have a corporate environment where you have like this one magic admin user that can connect everywhere. And if you find that out by brute forcing or by luck or by whatever, then basically you can just send him that, yeah, I'm that, please let me in. So that's kind of a cool feature to have. Okay, so now 2 demos worked. I have a last demo that probably will fail terribly, otherwise I'm too lucky. So, mentioned before, last feature that can be used for this user ID feature is Global Protect. Now, Global Protect is a VPN solution with support for mobile devices. It includes support for SSL VPN and for IPsec. And it works like you have the client software available for all the popular systems. So you have for desktop clients, you also have it for all the mobile platforms. And you can also set up it that you use Global Protect without the VPN functionality and just use like the clients to authenticate, because if the client uses like this Global Protect authentication in the internal network, then they will have a valid user ID mapping. So you are not restricted to only use Global Protect for VPN. Interestingly, if you look at Global Protect, you can see that everything that has to do with the SSL VPN and also all the configuration APIs, or like, so basically, for example, the mobile app will report if the device is jailbreaked, so it has like a jailbreak detection. And if you look how this works, it connects to the SSL port used by the SSL VPN and Global Protect and calls a special URL and send it report. And all of this is again implemented with AppWeb3 and PHP. And this, if you use Global Protect and use Global Protect in a way that you can support VPN connectivity, this stack will be exposed to the internet. So this is like the most interesting attack surface, because it's basically just a VPN server. And there is some functionality you can at least like, so you can call all the URLs and all the APIs. Of course, most of them will simply fail because you are not authenticated correctly, but you have kind of a code surface you can interact with. And it turns out some of this code isn't exactly the most stable. So quite early, I discovered the simple denial of service vulnerability that is triggered by a lot of A's in the password. So you just send a password consisting of something like 50K A's, and the box so the web server of the box just crashed down. And I was wondering, why is this happening? And the joke is that it uses unescaped string for XML, and the unescaped string for XML function decides to dynamically allocate memory, not using like a malloc, so that's allocated on the heap, but instead it uses the stack for this. And on my small MIPS 64 device, the stack size is heavily limited. So if you start allocating like 50K of stack space, you will access invalid memory and the box just crashes. Depending on what kind of architecture you have, this is also might be exploitable, but we continued looking for more interesting bugs that can also be exploited on this device. So the next thing we noticed, and this one is quite interesting, so Global Protect uses cookies, and these cookies are encrypted. And if you look how they are encrypted, it uses something called the device master key. A shuffled version of the device master key, but this shuffling is simply to reverse. And by default, this device master key is Palo Alto with a couple of numbers in between, so not exactly random. And so if you set up the system normally and you don't follow the hardening guide or you don't look at the hardening guide, this password won't be changed. And from my understanding from the documentation, it basically tells you, yeah, this is used to like encrypt configuration files lying on the system, which doesn't sound like it's too interesting. So if you don't change it, you probably don't know that now all your Global Protect cookies can be faked by an attacker. And this has kind of opens up the possibility for very interesting attacks. We couldn't like proof of concept the whole authentication bypass, because then you need a more complex setup with multiple Global Protect gateways and stuff. So I would have needed a couple of more of these devices, which I didn't get the money for, so that failed. But so this is something you might want to look into. So definitely change the device master key. to be fair to Palo Alto, this is also recommended if you actually read like the hardening guide of these devices. And this is also the reason why this is not really considered a security vulnerability. So there isn't a patch, you just have to harden your configuration. So if you use Global Protect, please change your device master key, otherwise interesting things might happen to your cookies. Okay, but we still have like one open question left. We want to have remote unauthenticated compromise of the device over Global Protect. And the unauthenticated attack surface that you have is quite limited. Mostly this goes directly into these login functions. So even the stack-based buffer overflow or the stack alloca overflow I just showed you was in the login functionality. It was the password. So what's the second parameter we can influence in the login functionality? It's the username, so wait for it. We have the escape string for XML function. And that escapes the username you send to it before then sending it as an XML encoded IPC message to the authentication daemon I mentioned at the beginning. Now, the function itself does not perform any length checks, and the destination sizes stack is 1024 bytes long, but they use a SSL VPN field filter check function that checks the length of the username before. So this is they check that it looks like a valid username, let's put it this way. So you can't simply send like a lot of A's, that won't work. You need a much more advanced attack, I'll show you next. So how does this function work, this field filter check user function? It basically looks at the username and splits it into a user part and into a domain part. So if you have something like user at whatever, then you have a user and a domain part. For each of these two parts, it performs a function called to isValid UTF-8, which only returns true if it's consisting completely of UTF-8 characters without any ASCII characters. So you're not allowed to put ASCII characters in there, otherwise the function will fail. Then you have a length check, and after that you have a regex check that checks that the username only contains alphanumeric values. Interestingly, if you send a username that only consists of UTF-8 characters that are not ASCII characters, then the complete check user function simply returns true. And if you listened carefully, you might have noticed that the length check is skipped. So what might happen if we send a lot of A's, like the R, A with the dots at the top? So the German listeners know this letter. This is also an attack that's much easier to execute for German users because we already have the keys on our keyboard. So just send a lot of these special German letters and the box will crash again, because then, of course, you bypass the length check, you overwrite the stack buffer, and it's game over. So put this in your fuzzing lists, like a lot of A's is important. Now the question, of course, for this bug is remote code execution possible? And as it turns out, that's actually not quite as trivial as I expected in the beginning. So oftentimes when I find these kind of bugs, I'm like going back to my chef or to my boss and Enno, and I'm like, yeah, I have this really cool bug, it should be exploitable. So we just report it and then go on. And then like I'm 2 weeks before my talk and I still need to do the demo, and then it's starting to get exciting because you realize it's not that easy. So, way to code execution. We have a destination buffer that's a fixed size stack buffer. We don't have any stack canaries, so it looks kind of straightforward. The executable itself isn't position independent, so we always have some kind of code at a static location. And the libraries, so all the libraries just use the standard RSLR you have on a Linux system. Now, the problem with this position, this binary at a static location, that it's really, really small. It's actually something like 44 kilobytes in size, because it only contains like 10 functions that directly call into this main library. And the library is at a randomized location. So this will bite us later and make exploitation a bit more difficult. Now, it's running on MIPS 64, and I think that's the most interesting aspect of the whole exploit. MIPS 64 isn't that much documented in a way I found on the internet. It's configured as a big endian system, so the most significant bytes are the first ones. And it's the first MIPS system I ever saw that has something like non-executable memory. So by default, MIPS doesn't support non-executable memory, but they have, so this Cavium Octeon processor has a feature called execute and inhibit, which is basically DEP or the NX bit. So they actually support non-executable memory. And then the way they add support for 64-bit in like this architecture is kind of strange. Because if you look at the address space, all of it is 32-bit. So you only have a 32-bit address space. And also all like pointers, so normal function pointers you see in the program and you see in the normal registers are all 32-bit long. But what happens is, so the MIPS has a special register for the return address, and this one is 64-bit wide. This is, of course, kind of a problem because it will always have a lot of zeros in the upper half of the register, which makes it quite hard to override in the Stack Overflow. Interestingly, even the GNU debugger I use to write the exploit doesn't realize that this register is 64-bit long and kind of just strips the upper half away, which took me quite a time to realize that my debugger is lying to me and this register is actually larger than I expected. So the first problem we have is the username cannot contain any ASCII characters. This makes exploitation kind of hard because you can only use like this multi-byte UTF-8 values, so that definitely doesn't work. So what we can do is we use this user at domain split, use user, which is this UTF-8 string of arbitrary length, to fill up like the buffer, and then just the end is this alphanumeric ASCII string. So we still have to jump to an alphanumeric address, but at least we can use ASCII, so we can use like normal byte values. It has to be shorter than 250 bytes as well. Now, as I mentioned before, this 64-bit architecture and the return address is a 64-bit value and it's big endian, so you start at the beginning of the address, and the beginning of the address is completely zeros. So you have 4 0 bytes at the beginning of the address. A 0 byte is, of course, not alphanumeric ASCII, so you can't simply override the return address, or that won't work out. So luckily, if you look at these functions where this whole login functionality is called, you have a PHP context stored on the stack. So we are inside the PHP runtime environment, and the PHP runtime has like one central context object that is used for every call to PHP functions. And before this function with the buffer overflow returns, you will see you have this call to PHP body write, which is a PHP function and which uses this context. The context has a pointer to a function pointer. So it's kind of a lot of indirections. And the new value we have to put instead of the original context object has to be an alphanumeric pointer. So the only way we can do this is by performing a heap spray. Because basically, normally, you won't have anything interesting that supports like double references of pointers at an address in memory that is alphanumeric. So we looked at how can you like spray the app web3 heap. And fortunately, this web server is kind of easy to spray because so you just open a socket and send like 1 megabyte of arbitrary binary plop over the socket. And as long as it doesn't contain like these 2 new lines, then you just, the web server won't close the connection and you are fine, and this memory will stay allocated in the heap. And the idea we are using is that you just open a lot of connections in parallel, so like 200, 400 connections, send this 1 megabyte plop to the server, and then keep the connection alive by just sending like single bytes and keeping the socket alive. And this gives us around like 50% reliability to allocate our payload, so the stuff we want to allocate, at this address in memory, which turns out, so if you decode the hex into ASCII, it's an alphanumeric string. So we can override the context, the PHP context object pointer with this value, and it will point into our payload. Now, so we have now this overwritten context object, and we have this PHP body write function. And you can see, so this is output of the libphp library that's compiled for MIPS. And what's happening is, so a pointer is read out of the A2 register, which points to our heap spray. It's written in the A3 register. And then we start with the A3 register, read the value again in the 4.1 register, read from V1 and store it in T9. So finally in T9 there's a function pointer. And if we do it like this, so like basically our heap spray just points back to the heap spray at a different offset again, we can store the address of an arbitrary gadget in the T9 register, which gives us the possibility to execute like our own code or the ROP gadget. Because our own code, so normally on a normal MIPS device, so all these routers or stuff you would find like in your kitchen, this would be game over already because then we put the address of our heap spray in these registers, jump to it, and execute our own shellcode. But this is not possible because the KVM Nextgen processor, as I mentioned before, is the only one that actually supports non-executable memory, or the only one I ever played with. So we can't perform a simple heap spray of that. So what we need is ROP. So we need to perform return-oriented programming to execute our own shellcode. So the problem with MIPS ROP, so if you ever did return-oriented programming on like the Intel architecture, you can jump into the middle of instructions, of multi-byte instructions, and generate like new accidental code you can execute. So you can, even if you have only a small binary, you will find a lot of interesting code functionality you can reuse. For MIPS, this is not possible because all the instructions are 4-byte aligned, and if you jump into an offset, so if you jump into the middle of an instruction, the processor will crash. So you can't like find gadgets, or you can't only use code that's actually in the binary. Now, the only object that's at a constant address is this whole AppWeb3 binary, which, as I mentioned before, is just 44K in size. It contains only 10 functions, and all these functions don't do anything interesting because they just call into this randomized shared libraries. So finding like a suitable ROP chain that gives you arbitrary execution of MIPS shellcode is really hard. So what I did instead, I discovered 2 gadgets that allow me the creation of arbitrary files. Basically, we have this gadget, and when we jump into this gadget, we control both the S1 register as well as the S4 register. And this allows me to, so by controlling the S1 register, which points to our heap spray again, we can put an arbitrary value again in T9. And by controlling the S4 register, we can set an arbitrary value into the A1 register. And the A1 register is the second argument that's passed to the next function. And what we are now doing is we jump to the MR start logging function, which is a function that's used by this AppWeb server. And it's basically, normally it initializes like all this logging procedure. But the side effect of this function is that it just creates a file at the path stored in the second argument. So now this whole buffer overflow, heap sparing, return-oriented programming just gives us the possibility to create an arbitrary named file somewhere on the file system. So as it turns out, luckily this gives you the root shell because we can combine this with another local bug. I can't describe it in too much detail because it's not patched yet. But in the end, it will pass this file, and if you include like special characters in this file name, you can do a command injection with that. And because the tool doing the parsing runs as the root user, you get like this automatic local privilege escalation to root included in this. And by combining this, so it's kind of interesting because if you would just, like if you would stop here and find a ROP chain, then it will come out with a nobody shell because again, the VPN service is running as nobody. But instead, triggering another bug that's only reachable locally normally, we can get a remote root shell. And I also have a demo for that. So this one, as I said before, the heap spray is kind of reliable. So it sometimes works on the first try, sometimes I need to try a second time. So hopefully you don't have to wait too long. So again, I have a reverse shell, and I start the SSL VPN exploit. So again, we are coming from the internet, unauthenticated, and attack this device. So it's like the perfect bug to exploit this. And you can see the pews are the single connection attempts, so we are doing the heap spraying. And after the heap spraying waits, we have to wait until, so possibly it's like a minute we have to wait because it's like a cron job that's triggering the local privilege escalation attack. So it might take a minute after the server crashes before we see like the reverse connection coming up on the right-hand side, and then we should have a root shell. So this should happen. After we've created the file, we just let the web server die a horrible death because we don't repair it, so it just crashed, but the file is created. And now, if I'm lucky, we get the connection. If I'm not lucky, we have to do it again and again and again. So then you might miss your lunch break, but that's okay, I hope. It takes until a minute, so I'm kind of hoping it works. Yeah, I should have opened Minesweeper or something like that.
As a script, there's a line which counts down from 60 to...
Yeah, that would be a good, right. I should have just slept and then count down, but I can do it like by hand. It's like 10, 9, hopefully. Ah. Yeah, and now we can see we're actually root. So this is like complete remote ownage, completely unauthenticated of an unpatched device. And I like, so, I mean, it's a cool bug, I think. Okay, so all the demos worked, so now I'm like kind of excited, and I just have to do like the final recommendations and the summary. So, step 1, isolate the management interface. They are very feature-rich and they are hard to secure completely. Step 2, if you use user ID for security-critical filtering as opposed to like business internal filtering between different business divisions or something, you might want to do something with strong authentication or something that supports it. And we don't recommend it to isolate the management interfaces because then we have like, if you have a bug in user ID, you bypass the isolation, you exploit the management interface and the bug is game over. So this is kind of, think about that. But you are already good to go, or it improves the situation a lot if you disable client probing. So you should never use client probing in a security-sensitive environment. If you use the user ID agent, use a host-based filtering mechanism to only allow the firewall to connect to this user ID agent. Change the master password so you are protected against this global protect cookie attack, and just keep your system updated because Palo Alto was really professional and responsive to our security contacts. So we are really happy the way Palo Alto handled this. So it was a really professional response, and patches are released for like the most critical of these vulnerabilities. Of course, it shows that if you have a firewall that is not just simply a stupid like packet filter, if you have more features, then you have a bigger attack surface, and this, of course, leads to more vulnerabilities. While these vulnerabilities are not really great, I mean, you saw them, it's not exactly the most great thing to have on your device, we are kind of positive about the response from the vendor, and it shows they have like the right mindset, and we are very positive about the future progress. So we hope that this was kind of a wake-up call, and in the future you won't find such vulnerabilities anymore in these devices. So thanks for your attention. I think we have some short question and answers. Yeah, so feel free to ask any questions.
Yeah, please feel free. So, wait.
Thanks for this. One question here. From the devices that you saw, are things like certificates or SSH keys generated upon installation, or is this also a default value, like a house of keys problem?
So like the authentication, you have to submit your own password and so, and we didn't see any signs of this typical backdoor support passwords or something, so we didn't see any of that. device will pop up like an SSL certificate, but this is configured like on installation.
So it is unique for device, for each device. Great.
So this
That's
seems to be kind of key.
Fine, thanks.
Any more questions?
Yeah, up here.
Okay.
You said that they have a feature that aligns the user with an IP address. So can't you just spoof an IP of the admin if you kind of just brute force the IP address, or?
So that's like, of course, if you are like in the same network segment as the admin and you have a DHCP server and you like burn the laptop of the administrator and the DHCP server gives you the IP address, you might have a time range where you can use like the permissions or the policies that are set for this admin users. There's no way around that.
And what you said with the UTF-8, was this kind of a bug that they didn't apply the length check there, or did this have any intention?
I'm not sure. I think it's a simple bug, but of course it's kind of hard to like. So they didn't want to do like the regex because you can't use like the alphanumerics check against UTF-8 characters. That wouldn't work. So they needed to skip the regex, and then they probably skipped the length check by accident. At least I think so.
Okay, so Felix, one. Yeah. Wait.
Yeah.
wait. No one understands without the mic.
Do you see a normal Linux distribution on the base operating system, or do you? They're using their own stuff?
No, it's kind of a stripped down Linux system. So I'm not exactly sure what distribution it is, but it looks kind of standard. It's probably something CentOS based or something.
Okay, thank you.
Okay, so was last question. Thank you very much, Felix. And I think it's time for lunch. So see you after lunch break.